Okay, nerds, so today we're going to start chapter 9, and chapter 9 is all about rational functions. And rational functions are everybody's favorite F word, fractions. Rational literally means fractions in mathematics. So if we say a rational number, what we're talking about is a number that could be represented using a fraction. So what is not a rational number? An irrational number. Irrational numbers are like root 2, root 5, pi, e. These are all irrational numbers. Rational means can be represented using a fraction with nothing but integers in it. And a rational function or rational expression is anything that has an x, or actually anything that has a variable in the denominator. So we're going to be dealing with a lot of fractions. And it's going to use one of your absolute favorite F words in every question other than fractions, factoring. And I'm sure that that has you thinking all kinds of other F words as well. Like, fantastic. I friggin' love fractions. It's going to be so much fun. All the F words, okay? Friendly, yes, another good F word. I know I'm always calling people friendly when I'm driving. Friendly you, things like that. So, today we're going to be focusing on multiplying and dividing our rational expressions. We're dealing with fractions, folks. Multiplying and dividing fractions. Hopefully you remember how that mechanic works from elementary school? 6th grade? I don't remember when you learn how to multiply and divide fractions. I don't remember. But in case you have forgotten, when you multiply fractions, you just go straight across the top, straight across the bottom. Multiplication. Boom. One fraction. When you divide, you do the whole keep, change, flip crap. Where you keep the first fraction what it is, you change the division to multiplication, and you multiply by the flipped over fraction. Keep, change, flip. It's like saying dividing by 2/3 is the same as multiplying by 3/2. You multiply by the reciprocal. Keep, change, flip. Which you'll see when we get to the back of the notes. Okie dokie. Let's go. Our job is to just simplify the expression. And the way we're going to do that is we are going to factor everything into whatever we could. We need to see all the individual factors, all the multipliers. I mean, if I gave you, trying to find something I can write on, if I gave you, boop, boop, a fraction like this, you would all tell me it's 1/2, right? But why is it 1/2? Here's why it's 1/2. Because the number 12 can be written as 6 times 2. So we're going to be breaking our polynomials into factors, so that way we can cancel 6 divided by 6 is 1, and reduce. We're doing the exact same thing. We're going to be breaking polynomials down into their multipliers, and anytime we can, through division, we'll cancel stuff. Okay? Math doesn't change, it just looks different. Anyway, we have to figure out how to factor this thing on top. Looking for the two numbers that multiply to -12 that add to -4. Hopefully that's easy enough. It's going to be -6 and +2. Almost like I knew a 6 and 2 was coming up, Anyway, -6 and +2. X minus 6 and x plus 2. Like that. And the bottom one's a cubic. Oh no! I'm going to do rational root theorem and all that stuff that we just did in the last chapter. No, actually, because this one's GCF includes an x. So it will be a quadratic. And as usual, when you're factoring, you're always looking for a GCF first. And this one's GCF happens to be 2x. So we're going to pull a 2x, and it's going to give me an x squared minus 9x plus 18. Then we need to factor the quadratic that's on the bottom if we can. And we can. There are two numbers that multiply to positive 18 that add to negative 9. It's negative 6 and negative 3. Everything is factored. Factors are things that we multiply to each other. So up top, this stuff is held together by multiplication, and on bottom, this stuff is held together by multiplication. And when things are held together with multiplication, you can cancel things off of the top and bottom like I did here. But remember, canceling with fractions, which are division, is always going to give you a 1. Something divided by itself is a 1. We go, okay, cool. Well, x minus 6, whatever number that is, because we don't know what x is. X minus 6 divided by x minus 6 is going to give me a 1. So this and this cancel each other out. And that leaves us with this result, a simplified expression, x plus 2 over, and don't distribute, 2x times x minus 3. Once something is factored, don't undo it. You want to leave things factored. It makes them much easier to graph, and we will be graphing these later in the chapter. You gotta find my here it is, graphing calculator. Okay, now, can someone please tell me, and it's okay and it's obvious, what does equals mean in mathematics? Same as. And it's more powerful than same as. It's exactly the same as in every single way. What is written right now says that this fraction is exactly the same as this fraction in every single way. Correct? Okay. You don't need a graphing calculator to do this work. I'm using a graphing calculator in the video because what I was going to do in Desmos is very important to be seen. So I'm going to do it on the graphing calculator so it makes it into the video. Okay? Let's see. Y equals, good, I don't have anything there. I'm going to graph this. Let's see, x squared minus 4x minus 12 over 2x raised to the third minus 18x squared plus 36x. And then I'm going to graph this. And this is color. The first one will graph in blue. The second one will graph in red. Actually, tell you what, let me clear it. Let me show you this thing's graph. Okay? Zoom 6. So here's the graph of the original expression. Whee! Whee! Hold on, it's not done yet. There we go. Now, the graph did not come to an end at either one of these things. It's just that this calculator, it can't draw the vertical line at x equals 0. That's an asymptote. So if I graphed it on Desmos, you would see a curve get really, really close that goes down forever here, and a curve that gets really, really close but goes up forever right there. Okay? It has a vertical asymptote at x equals 0, and it has a vertical asymptote at x equals 3. Which makes sense, because look, if you put x equals 0 right here, you're trying to divide by 0, aren't you? And if you put x equals 3 right here, you're trying to divide by 0 again, which is why it has those two vertical asymptotes, right? Comfortable with that? Okay. Don't worry, we're not graphing right now. I'm just showing you something very important. Now, I'm going to go down and I'm going to graph the result. Because these two things are not exactly the same. This will be waiting for you as an answer choice on my test, though, and it'll be worth half credit. Because they're not the same. Let me prove it to you. It's now going to graph the red graph on the same screen as the blue graph. And we expect them to be the exact same graph, don't we? Uh-oh. Those look like they're the same. Tell you what. I'm going to use a feature of this calculator that shows me the coordinate pairs, x comma y, instead of the lines, okay? Looks like they're the same, doesn't it? I mean, all the y values seem to match, right? I mean, I sure hope they stay matching. I mean, if they stay matching, maybe I'm wrong. Maybe they are the... Oh my goodness. This red graph exists somewhere where the blue graph does not. So can we agree, based on what you see here, that this and this are not 100% identical? Something clearly went wrong. And let's talk about what it was. I feel like that is more powerful to see on Desmos, but I needed it in the video so that you could see that, yeah, they're not the same. What went wrong? You all know that this is the original question, yes? And you all agree that the original question factors to this, yes? How many zeros does that denominator have? Meaning from the last chapter, zeros are solutions. How many zeros does that denominator have? 3 of them. Of course, are you allowed to divide by 0? No. What that tells us is there were 3 numbers that we were never allowed to let x equal. And those 3 numbers were x equals 0, because that would have made me divide by 0. X equals 6, because that would have made me divide by 0. And x equals 3, because that would have made me divide by 0. Then we simplified. And the final answer says x can't be 0 and x can't be 3. But it no longer shows us x equaling 6 is a no-no. But since we all know that this is the actual question, we all know there are 3 no-nos for x. X can't be 0, my final answer represents that. X can't be 3, my final answer represents that. X can't be 6. And since my final answer doesn't show me that x can't be 6, I have to say that. Now they're 100% identical. Because I have just said they're the same as long as you don't let x equal 6. You see, what happened was the calculator can only color in pixels. But the graph, my original blue graph, which is why I did this example in blue, the original blue graph has what we call a hole in the graph. A removable discontinuity. That's the fancy words for it. It's literally a single point in space where the graph didn't exist. And that single point in space where the original graph didn't exist was at 6, 2 over 9. This one exists at 6, 2 over 9. This one does not. Therefore, we have to go, don't you dare try to use x equals 6. Now they're perfectly the same. Basically, if you cross an x off the bottom of the fraction, you now have to mention something x is not allowed to be in the final answer. Every time you cross an x off, that's something you have to mention at the end because the resulting expression will not show you that. Cool with that? We just need more practice, and I feel like you'll be a lot more comfortable with the idea. And hopefully the graphing calculator did just as good a job as Desmos would have in showing you why they're not the same until you say that. Like I said, that answer's worth half credit. That answer's worth full credit. Let's do another one where we simplify. And the reason why we're going to do another one where all we do is factor and simplify is, the lights just flickered, is because this one has a number in front of x squared that is not a GCF. So this one time, and one time only, I'm going to show you how to do this Algebra 1 factoring question again. Even though I did it earlier in the year, I'm going to do it again. Move on to green. The top is a special case, perfect square minus perfect square. You should all be masters of that now because of the last chapter. A squared minus b squared is always going to factor to a plus b times a minus b. Don't tell my wife I put orange and green on the same question. But to factor something that has a number in front of x squared, you figure out what 2 numbers will multiply to a times c. Here, our a times c is 2 times 15, which is 30. And what those 2 numbers need to add to is my b value, which is a negative 11. And yeah, there are two numbers that multiply to 30 and add to negative 11. Those two numbers are negative 5 and negative 6, right? Those add to negative 11, they multiply to positive 30. What you're going to do is you're going to take your negative 11x and you're going to write it as a negative 5x plus a negative 6x. Or you could just say negative 5x minus 6x. It doesn't matter how you say it. But you're going to split that middle term into these two things. And I won't show that again because we did it earlier in the year. And now you get to factor by grouping because that has 4 terms. And we practiced factoring by grouping in the last chapter. And we did it earlier in the year when I taught you this way back in chapter 2. The top is still giving me 3 plus x times 3 minus x. On the bottom, though, the first purple group has a GCF of x and only x. That'll leave behind a 2x minus 5. The next purple group begins with a negative number. And anytime you begin with a negative number, you need to pull a negative GCF. So I'm going to say that GCF is negative 3. That will get us to 3 plus x times 3 minus x. And on the bottom, I've got 2x minus 5 times x minus 3. So everything is broken down into their factors. And what I'd be trying to do now is cross off factors that match on the top and bottom. Well, the way it sits, no factors match on the top and bottom, do they? But gosh darn it, 3 minus x is almost the same as x minus 3. I mean, the subtraction is just out of order. Now, I can't just switch. 3 minus x is not the same as x minus 3. And that's really easy to prove. I mean, pretend x is 0. That would give you 3 and negative 3. They're clearly not the same thing. But wait a minute. Whoa, 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 whoa. I can reduce 3 over negative 3, though, can't I? What does 3 over negative 3 get me? Negative 1. Yeah, Nick, you know what that means? I must be able to reduce this, but the result would be negative. That's right. This is written out of order. You could have thought of this as saying negative x or plus 3, right? And doesn't that begin with a negative term then? And I told you that anytime something begins with a negative term, you've got a negative GCF. I just said those words. Even if that negative GCF is just the negative 1 that Nick told me a second ago. And if you divide a negative 1 out of this, it will give you this. If you ever want to switch the order of subtraction, just pull a negative 1 out. That'll always switch the order of subtraction. And now I have a factor that matches on top and on bottom. X minus 3 divided by x minus 3 is 1. I just canceled an x off the bottom of my fraction. I eliminated a no-no. I created a hole in my graph. So when I write the final simplified version, by the way, 3 plus x really annoys the pants off me. I'm just going to call it x plus 3. No math is happening there. It's that the order of addition doesn't matter. Okay? So I've got my negative sign. There's no reason to write the 1. It's x plus 3 over 2x minus 5. The parentheses aren't necessary on the bottom anymore. And I just have to make sure that these two things are exactly the same. And since this graph can't exist at x equals 3 because that makes me divide by 0, this graph also can't exist at x equals 3. And there it is. So before we start actually multiplying and dividing these things, I need to know what I can help you with as far as questions, comments, concerns, what ifs, why didn't yous, anything like that. How comes, the what happened wins. Let me hear them. Let me help you. Yes, ma'am.
I'm just really confused how you split the 11.
So how we split the negative 11?
Yeah.
You have to do A times C,
Okay.
where A is 2 and C is 15. We get that number is 15, and we have like that. Essentially what we're doing is we're pretending that bottom thing didn't say this. We're pretending, take the 2 and multiply it to the 15. We're pretending it said this. Of course, it doesn't say that. But the two numbers that multiply to 30 that add to negative 11 are negative 5 and negative 6. But I can't just write x minus 5 times x minus 6. Because if you do x minus 5 times x minus 6, it's going to end in a positive 30, and it's going to start with an x squared. So what we do then is we say, I'll break that number into those two values, but they have x's next to them. So yes, it was negative 5 and negative 6. It's negative 5x and negative 6x, which allows me to factor by grouping. And that will always work. Okay? Yes? It's like you missed this entire thing I did in purple with me asking Nick what 3 over negative 3 was, and it was negative 1, right? Okay. Anytime this 3 minus x is written out of order, correct? So this is it written in correct order. But it's weird when things begin with a negative number. And I told you, anytime you begin with a negative number, say you have a negative GCF. I'll say it's negative 1. So I factored out a negative 1. I divided out a negative 1. That'll make that positive, and that'll make that negative. That's how we do it. If you ever need or want to switch the order of subtraction, you might want to write that down. If you ever need or want to switch the order of subtraction, you factor out a negative 1. That will always switch the order of subtraction. That's how we do that. And more questions. Any more? It's good that we get these on the video. No? Okay. So we did this last year. You learned how to factor, not last year, last quarter, actually. We did some of it last quarter, but I taught you how to do it in chapter 2 way back at the beginning of the year. You learned how to do something similar to this in Algebra 1. You learned some kind of factoring technique. Pick one, be good at it. This is Algebra 2 Honors. I have to assume by now you can factor a quadratic. If you know you're bad at factoring things like this, please find practice online. There's Buku. Or ask me to give you some. I have a ton. Okay? Okay. Because this next one involves something just like it, but I'm not going to go through the process. I'm going to go immediately to its factored version. All right. X plus 4 is x plus 4. There are two numbers that multiply to negative 20 and add to negative 19, so I know this factors. I am older than dirt, so years and years and years and lots of practice have shown me instantly how to factor this, and it factors like that. I'm aware it might have taken you a little bit longer to factor it. You're going to use a method of some sort. That's fine, but I need the video to, cover the entire section of notes within our class period. Okay, the next one. 2x and 10 have a GCF of 2. And then we just have down here a 6. Cool. Okay. When you multiply fractions, you literally go across the top and across the bottom. Boink! You multiply everything just like that, okay? That means the x plus 4, the 2, and the x minus 5 could all be written on the top of one fraction with multiplication dots in between them. Likewise, the 4x plus 1, the x minus 5, and the 6 can all be written on the bottom of one fraction with multiplication dots in between them. And if they were one fraction with multiplication dots in between them, then anything that was on the top and the bottom as a multiple would cancel out, right? That means this x minus 5 on the bottom and this x minus 5 on the top cancel each other out. Since I just crossed an x off the bottom, I am going to have to list a domain restriction in my answer, because my answer will no longer show me that x was never allowed to be 5. And before we actually multiply them, 2 over 6 reduces. You can divide the top and the bottom both by 2. So this 2 divided by 2 is 1. This 6 divided by 2 is 3. There. Does this create a domain restriction? No, because I did not cross off an x right there. It's only when you cancel off x's. Our final simplified form is, well, all that's left on top is the x plus 4. On the bottom, I have a 3, and I have a 4x plus 1. Then we have to say, oh, by the way, you're not allowed to use x equals 5. So multiplying these things is no more difficult than what we did in the first 2 examples. You might have to factor more than one thing. Woo. Luckily, all of last chapter was factoring, right? You should be very good at factoring. It's almost like they planned it that way when they picked the order of us to learn, right? Because this is chapter 9 following chapter 5. Would you like to ask me anything about that one? Yes.
So you don't multiply with x minus 5 first? You just cancel out right there?
Yeah, I mean, if you want to write it all as one fraction, you can.
But it will get canceled out?
Yeah. Because here's what's going to happen, and you definitely wouldn't distribute a FOIL, because then you'd have to factor again. Don't do that. No, I mean, you write it all in one fraction. I mean, you just pretend you've got a 2, you got an x plus 4, and you got an x minus 5, all on the top of this fraction now. So anything that matches top and bottom, they cancel off. There's no reason to actually write it as one fraction until you've simplified. This is technically called cross-canceling, and it works when you're multiplying and something matches on the top and bottom. You don't have to know the vocabulary of cross-canceling. If you're more comfortable with it, you could easily write it all in one fraction and then cancel. Doesn't matter. I just didn't want to have to write one more thing. Just being lazy. But yeah, no, you don't have to write it as one fraction. I like to simplify before I make one fraction. And please don't ever go through any distributions in your final answers. Leave your final answers factored. Okay? You can combine like terms and things like that, but leave your final answers factored. It's easier for graphing purposes, which we will be doing later in this chapter. Next, factoring some more. I'll write this one in orange. The first one's written out of order. What does that tell you about your GCF? It's negative. It's out of order, so the GCF is negative. We're going to say the GCF is negative 3x. Dividing both these things by negative 3x, remember, it's going to switch the order of subtraction, so I'm going to say it's going to give me an x minus 1. On the bottom, the two numbers that multiply to negative 5 and add to 4, x plus 5, x minus 1. Almost said minus 4 for some reason. Next fraction. The two numbers that multiply to negative 20 and add to 1 are 5 and negative 4. And now I've got this 3x on the bottom. The way it sits, there are 3 numbers that x is not ever allowed to be. X can't be negative 5, x can't be positive 1, x can't be 0. We see that any one of those numbers would put a 0 on the bottom of a fraction. Not ever allowed. X can't be negative 5, x can't be 1, x can't be 0. Now let's start the canceling process. Hey, x minus 1 divided by x minus 1 cancels. Okay, I'm going to have to mention x can't be 1. And, oh, the x plus 5s cancel. I'm going to have to mention that x can't be negative 5. And, hey, look at that. 3x cancels 3x. Now the negative sign sticks around, but 3x over 3x is 1. There's nothing left on the bottom. All we have is a negative sign and an x minus 4. But we did know that there were 3 numbers that x was not allowed to be. x couldn't be negative 5, x couldn't be positive, well, 0, and x couldn't be positive 1. They don't have to be written in numeric order. I just prefer them to be written in numeric order. Wow, the entire denominator canceled out. That's nuts. It's crazy. Now, if the bell rings before I'm done with the notes, I'm going to pause it, and then I'm going to finish it after you're all done. So you might want to make sure that you catch the end of that video tonight, okay? Or just don't pack up early. Luckily, the last two questions are exactly the same skill set, so I'm not really worried about it even making it into the video. It's division. And you might be thinking, oh my gosh, division, it's so crazy hard. Oh, this is third period, isn't it? Not fourth period? Shoot, I'm good. I thought this was fourth period. Never mind, we Gucci. We're good. Yeah. I was wondering where all my time went. You might be thinking, division's so hard. But it's not. Because a good old keep, change, flip. Keep this, what it is, change that to multiplication, flip this fraction over. And now it's no different than what we just did on the front. That's all that makes this question special. At this point, we're going to factor everything. Cycle back to blue. The two numbers that multiply to negative 15 and add to 2 are 5 and negative 3. Yes, 5 and negative 3. So we have x plus 5 times x minus 3. Now on the bottom I have an x minus 5. Nothing going on there. The next fraction, I just got an x plus 3. But x squared minus 9, you should recognize that from the last chapter. That is the difference of two squares, a squared minus b squared. Factors instantly to a plus b times a minus b. Of course, b is 3. At this point, everything's factored. We start looking for things we can cancel. Things that match on the top and the bottom. The x minus 3's match. I'm going to have to mention that x is not allowed to be 3 then. Oh, the x plus 3's match. I'm going to have to mention that x can't be negative 3 because of that. Does anything cancel here? Nothing cancels. These two things are actually 100% different. There's nothing we can do to make this one say plus between two positive numbers, or this one say minus between two numbers without other negatives. There's nothing we can do. So it is fully simplified when you say x plus 5 over x minus 5. You just have to mention the two numbers that x is not allowed to be. Positive or negative 3. You see, because this is addition and this is subtraction, 5s can't cancel. I said you can only cancel things out between factors. And factors are held together with multiplication dots. Okay? All right. And then we only have one more, unless you have questions about that one. Nothing? Okay. Then we have one more. Scoot. What did I do the next one in after I did blue? Was it green or purple? It was green. Okay, I'll cycle back to green then. What? First, keep, change, flip. Keep the first fraction alone. Change the division and multiplication, and flip the second fraction over. You're actually just supposed to say, instead of dividing by a fraction, we're going to multiply by the reciprocal. That's the actual words. Keep, change, flip is a cutesy thing that people say because it helps them remember a rule. The rule is when dividing by a fraction, you multiply by the reciprocal. It's no different from the last question or anything on the front now. Factor everything that you can. What did I say I was doing? Green? 7x is 7x. Can't do anything. However, 2x minus 10, those are both even numbers. Got a GCF of 2. Might as well pull it. Undistribute that bad boy. We just did x squared minus 11x plus 30 on the other side of the notes. Well, kinda. We said that the two numbers that multiply to positive 30 and add to negative 11 were negative 5 and negative 6. But this time I can actually just write x minus 5 times x minus 6. And on the bottom, GCF of x. We're finished factoring. Take a peekaboo. How many numbers are no-nos for x? Three. X can't be 5. X can't be 0. X can't be 6. Remember, anytime there's an x outside of parentheses multiplied, its solution, its 0 is automatically 0. And you can't have 0 on the bottom. So there are 3 numbers that x can't be. Let's go ahead and start simplifying and see what happens. First and foremost, I see this x minus 5 canceling this x minus 5. I'm going to have to say x can't be 5. I see x minus 6 canceling x minus 6. I'm going to have to say x can't be 6. Uh-oh, wait a minute. X divided by x is 1. I'm going to have to say x can't be 0. This fully simplifies all the way down to the number 7 over 2. But the graph of y equals 7 over 2 is a horizontal line that goes on unbroken forever. This looks like that horizontal line, except it has 3 numbers that x can't be. So in order for them to match, we have to say all of those numbers since our function no longer shows them to us. And I'm just going to put them in numeric order. X can't be 0, 5, or 6. Do you have any questions about the concept, about this question, about anything we did? What ifs? How comes? Could you have? Any of that kind of stuff? Nobody. All right. Well, then I guess we're all just power nerds then.